here, starting the show. Welcome back, everybody. Hello. Having late lunches, snacks? Yep, okay. How's homework going? Good. Any questions that I can help you with? That's what we were just talking about. No? Okay, due tomorrow. So let me know if anything comes up. After today, I will figure out what we're going to do for our next formative assessment and let you know when that is up, hopefully either later this afternoon or tomorrow morning at the latest. Really? No questions? We're good? Good on proportionals? All right, cool. I'm still working on your next homework. It is not done yet, but I will let you know when that's up. That will be due in 2 weeks from tomorrow, so you'll hopefully get that up by the end of the weekend at the latest. Let's see, we don't need this handout right now, but we do need some other stuff. So here we go. What were we talking about last time? Do you remember? Here. There. We can all look at the pretty beach while we remember what we're talking about last time. As usual, I will accept words, gestures, phrases. The thing that I learned 10 minutes before class, yes.
With the cool graph that you
With-
got from Wikipedia.
With the cool graph that I got from Wikipedia. I believe you were talking about the beta distribution.
Yes, that one.
Yeah,
Beta.
yeah. You remember that? That's good. What is beta used for? What kind of outcome?
That's what I don't remember.
Okay, that's fine.
I just like.
That's why
the
we're
graph is
reviewing.
what I remember.
Yeah, so broadly construed, in terms of regression type models for predicting things that aren't normal, what have we covered so far this semester? Counts, right? What is special about counts? What do we have to worry about? Ceilings, floors, or both? For counts? Sorta? Floor. Counts are bounded at 0. Now, why do you say sorta? Because I think you might be talking about the answer to my next question.
It's like there's a reasonable stopping point.
There's a reasonable stopping point?
There's not like you can't like a lot of times it's not like 1.5.
Okay, counts are discrete.
Okay.
I will take that, yes. The count distributions, which ones did you learn? I can think of 2. Poisson. And why does Poisson not work in real data very often? The mean and the variance are the same thing. So what do we do to it to fix it? Stretchy. What's stretchy called?
K.
K is the stretchy parameter in my notation. Negative binomial. Yes. Yes. And what is the link function we predict counts with? There's only one that we did in our class. I've only seen one other one besides that. Is it logit? For counts? What's the difference between logit and log? I know, and we're reviewing. That's what we're doing. Okay, logit is say it with me, the log of the odds of the probability of 1 is a logit. So a log is just a log. It's a button on your calculator. But what does it do? Why do we use a log to predict a count? Bounded at 0. So if we predict the log, are logs bounded at 0? No, logs go on forever and ever. So we can have our linear model that goes on forever and ever. When we back translate, what does back translate in stats terms? Inverse link, yes. If we unlog it, or exponentiate it, right, then we get back to the actual predicted counts. Yep, that's one thing we did. That's what the homework is that we're working on. The backstory of the homework I decided is going to be yet another preschool adventure. I write about what I know. My son is currently in a therapy type program that we call food school because he is a super duper picky eater to the point that I'm worried about malnutrition. Like he's going to try and kill himself by eating only mac and cheese for the rest of his life kind of thing, even though he's still fine in terms of size. And his pediatrician recommended this program where it's basically a desensitization of food. So they give him food, some of which they know he'll eat, some of which they don't, and they ask him if he's willing to look at it, touch it, play with it, put it next to his face, have it touch his lips, lick it, and then actually put it in his mouth, and then actually eat it. Like, that's the culmination of this thing. So he's in this thing called food school. And the teacher asked me how it was going at home, because we're supposed to be reinforcing all these things. And I had a moment where I'm like, I'm not being very consistent with that, because by the time dinner rolls around at 6:30, I'm just like, fine, have your mac and cheese. I don't want to fight. Like, I'm tired, right? I just want you to eat. So the homework is going to be about the effect of food school on picky eaters and how that potentially interacts with full-time jobs of the parents of these children. That's going to be the story. It's not quite done yet, but it's going to be a count outcome, the number of foods that they are willing to try. That's the count. So good. That was a good place to start. That was a nice segue. So we did counts. What else have we done? What was your first homework about? That was number 2. First homework. Binary. Yeah, what's special about binary outcomes? Yeah, they're Bernoulli, the end, right? What kind of link do we need for binary? What do we have to worry about?
We need to transform 0, 1 into all possible.
Transform 0, 1 into all possible. So there's sort of 2 phases, right? First step is the conditional mean of 0, 1 is probability. Like, that's the thing we're trying to predict. Probability is bounded between 0 and 1. So we got to transform probability into something that is unbounded, and that is our best friend, who? Logit. Give me another one that does the same thing. Probit. What's the difference between Logit and Probit? 1.7. They do the same thing. What is a Probit? Remember? It's a z-score. It's the z-score that goes with the area to the left under the curve, if that's the p-value. So z's have a middle of 0. They have a variance of 1. If you convert from the z from a logistic distribution that goes with Logit, it works out that there's a conversion of 1.7 and they map onto each other. There were 2 others that you could potentially use for binary. Remember those? Log and its friend, complementary log. And they are asymmetric links. I don't remember which is which off the top of my head. I could look it up. One of them is for outcomes that are more frequently 1. Another is for outcomes that are more frequently 0. So those are the 4 that you would see for binary. Then what did we do? What else? There's one other kind of outcome that you're currently working on homework about. Ordinal, more generally categorical, right? Outcomes where you have more than 2 categories, but they're not numbers. So there's 2, those fall into 2 flavors, ordinal or nominal. Ordinal's order, nominal's not. What kind of distribution goes with categorical outcomes? Multinomial. What kind of link goes with those? Special flavor of Logit. Because Logits are for binary outcomes, right? How do I translate a Logit into something that is for ordinal or nominal? C-Logit. Which one is for that? That's ordinal. What does C stand for? Cumulative. How does that work? How does it work?
Whether it's like 0, 1, 2.
That.
Basically making it kind of like dichotomous.
It's creating a series of dichotomous, what I call submodels, because they're all working together to describe the outcome. How many submodels do you need?
Depends on how many categories.
Depends on how many categories. What if I have 4 categories? How many submodels? 3. Yep, it's always n minus 1. If I had let me see here, let me pull up something. If I had, let's say I have a 4 category outcome. So I have y equals 1 or 2 or 3 or 4. A cumulative logit would do what? Submodel 1. I'm just going to say, what are we predicting? I'll do the first one for you. Y versus 2, 3, 4. Submodel 2. What do I type? 1, 2 versus 3, 4. Submodel 3. 1, 2, 3 versus 4. So each of these is binary. That's how we're able to still use a logit. The cumulative part refers to the fact that we have all the categories in each submodel. So the 1 is the higher category. And if you are predicting 2, 3, 4, that's an intercept, right? If I am predicting 1, what do I call that? Threshold. How are they related? Yeah, not 1 minus. That was a good guess though. And these are in logits. So it's minus 1 times one of those is the other. It would be 1 minus if we were in probabilities. So if I have a logit, say, logit intercept equals 2. That means my logit threshold equals what? Minus 2. Now if I go into probability intercept, how do I find it? E to the logit over 1 plus e to the logit. Yeah. I don't have many formulas memorized, but this is one of the few that made the cut. What does a logit of 2 translate into in probability? You want to find out? Let's find out, shall we? Good afternoon, Excel says. I hear you'd like to do some math. Why, yes. Yes, I would. E to the that over 1 plus e to the that. 0.88 and some change. Probability intercept, 0.88. That's the probability of 2, 3, 4. How do I get the probability of 1? Yeah, 1 minus 0.88. So yeah, they're related to each other, but it's minus sign in logits. It's 1 minus in probabilities. You can always get one from the other. Those of you who've taken IRT, what am I talking about? What is this called in IRT land? I know, Kofung, you know this. I think you're in this class right now, aren't you? Uh-huh. Have you talked about it yet? No? This is the graded response model. You haven't done that one yet? Okay, wait for it, because that's what this is. Yep. Do you know what the difference is? In IRT, the predictor of the model is latent. It's imaginary. In this model, the predictors are in our data set. That's the difference. Did that just blow your mind, Jeff? Give me that look like, what? No? Huh? Never mind? No? I'm not allowed to just call on people who make facial expressions? That was like a thing. But yeah, you can have imaginary variables as predictors. It's pretty cool. Come back next fall and I'll tell you all about it. Yeah. Yep. Okay, we're good with this? This one? Now, what if this was a nominal outcome instead? Can I do this? Will the software let me? Oh, it's be happy to do it for me. Would it make any kind of sense? No, no. So how does this change? How do my submodels change if these are now nominal categories that are unordered? I need a reference one. How about, let's make 1 the reference. 1 equals reference. So what's my first submodel? 1 versus 2. What's my second submodel? 1 versus 3. What's my last one? 1 versus 4. That's nominal. What is that link called? The words that this submodel system goes with. I'll take 2. There's 2 I've heard of it is called as. It's G-Logit in Glimix. Generalized is what G stands for. Isn't that a terrible name? That's this entire set of models. I call this baseline category Logit. That's another one that you'll see. Baseline category Logit. Yep. The take-home message when you're trying to describe using these models in papers, do this part for them. Explain to them how the submodels work, because you don't know that they know what it's called by the same words that you think it's called. So, an introductory paragraph explaining the submodels. In nominal models, all of the slopes are estimated separately across submodels by default. In ordinal models, they are not. So in ordinal models, the slopes are shared across submodels. That's what's known as a proportional odds assumption. If the slopes are different across submodels, that is a violation of proportional odds. And that's why we switched to Go Logit 2, because that was the one thing that allowed you to do that. And Proclogistic for that matter. Okay, so putting it all together, we've done binary outcomes, categorical outcomes of each of these 2 kinds. We did counts. What did we start talking about on Tuesday? Other things that aren't normal. Yes, this is the catch-all section. Like what? I would argue Likert scale things fall into this if you're predicting each item. If you're predicting a sum across items, then yes, that's what we start talking about. More generally, proportions. Yeah, you can think of it as a proportion. If you correct it to range from 0 to 1, you can think of those as proportions. What do we have to worry about in predicting proportions? Can we just put the proportion in a model and call it good? No. What do we need to worry about in terms of boundaries for proportions? A ceiling? Yep. Because what's the highest proportion you can have? 1 or 100, however, whichever decimal thing we're doing here. What's the lowest you can have? 0. So we need to understand that the slopes shut off, right? How do you make a slope shut off from both directions? Which friend is that? Yes, this is my Walk Like an Egyptian joke. It was 1986. It was a great album. It was the Bangles. They're wonderful. One of the first cassette tapes I ever owned. Yeah. What do we do? Yeah, Logit or log? Logit, yes. Log is for bounded at the bottom only. Logit is for bounded for both. So yep, we're back to Logit, and it's Logit, probit, log, complementary log, all those things. What's the distribution that goes with proportions? Is there only one? No. I knew of one until 10 minutes ago, roughly. This is where we're coming back to. Yep. So this is what we started talking about, is what to do instead. Proportions and rates is where we are. So, generally speaking, values are continuous over some range here, but they're bounded at the top and by the bottom. So here's the thing I knew about prior to 10 minutes ago. This is our friend Binomial. Bernoulli is a special case of binomial when there's only one event, like one trial, as they say. This one has the same limitation as Poisson, where the variance is a direct function of the mean without any extra parameters. So if you have a proportion that has more skewness to it, you could be in trouble. So that's where we get to choose something else instead. And Lexi, this is the picture you had in your head, right? Yeah. This is our friend beta. Beta can also be used for proportions, but beta does not include 0 or 1. I have never seen beta used in practice all by itself. Where this shows up is when you try to combine the two into something called a beta binomial. Beta binomial, the difference between regular flavor binomial and beta binomial is this thing right here. It's another type of stretchy factor. You can think of it the same way. It's multiplicative extra variance that shows up in a model. So it breaks the constraint that the variance and mean are tied together. And this is the new thing I learned about 10 minutes ago. Okay, so that's what we started looking at. This example. This outcome. Percent correct. With a big ol' ceiling effect. So we looked at an empty model to try and describe the way that this works. So what we're saying here, if we use binomial, is that number correct is the outcome that we're modeling. We have to tell it two things. How many events we have, like number correct, and what else? Feel free to read from the screen. What else do we need to know?
Number of items or
Number of total, some sort of denominator, right? And Kelly, you just found out that Stata will be happy to run binomial without a denominator, right?
I think so, yeah.
Yet another instance of software doing stupid things if that's what you ask it to do. Yep. So what the model is actually predicting is this thing right here, P, probability, just like in binary models. It's the probability of getting any one trial correct or having any one event, so and more generically. The mean to get to number correct, it's the number of trials times P. So it's a roundabout way of saying what the model is predicting is the logit of percent correct. That's what it's doing. Okay. Does that make sense so far? That's what we're doing. Just like in binary data, where we're trying to predict the probability of a 1. Well, in binary data, there is only one 1. In this, there is n trials opportunities to get a 1. The model is still predicting the probability of a 1. It just works out to be then percent correct. Or percent events, some kind of rate out of total. The difference in the code, you have to explicitly tell it the number of events over the number of total. That goes in Stata right here for the total and the number of events here. So the empty model I fit to make sure that I understand the parameterization. It returned a constant in logits of about 2.5. When you unlogit that, you end up with a percent correct of 0.92, which is exactly what we have in the data. Okay. Does that make sense? Remember empty models? Do we need to review this? Yeah, would be good. An empty model is a model that doesn't have any predictors. It's the jumping off point. If you don't know anything about a person, what is your best guess for their outcome? The mean. That's what the empty model predicts for all cases. So it is literally just spitting back your summary statistics of your outcome variable to you. In continuous outcomes, it spits back the mean as the intercept, and it spits back the total variability in the outcome as residual variance. Here, we don't have a we don't have a variance type parameter in binomial. Binomial says the variance is the mean times 1 minus the mean. That's what binomial says it's supposed to be. So it's an empty model just to verify that I know what it's doing. That is the point of this. It gives me confidence to get the mean back, because then I know that it's predicting the probability of a 1 as opposed to a 0, or any other permutation, but it's doing it in logits. This thing right here, Pearson chi-square over degrees of freedom, that's our index of distributional misfit. Right now it's 21, which is way high because we don't have any predictors in the model, so there's a whole lot of extra variance. And we added predictors.
Can you say what that is?
Pearson chi-square over degrees of freedom. That thing. It shows up here in Stata. It shows up down here in SAS. Yep. What's it supposed to be? 1. So the standard deviation from the residuals in the data over what's the standard deviation is supposed to be at that point on the mean, or on that point of the variable in the model. So if you have over dispersion that's not accounted for, that means your standard errors are going to be too small and your p-value is too optimistic. That's why we care. So we threw in some predictors. I have the main focus of interest in this data was a grouping variable, whether or not each child has a non-specific language impairment, sort of a general issue, or something that's specific, and mother's education as the covariate that someone is going to be angry with me if I don't control for. And that's going to be the model throughout the rest of this, because we're just focusing on the distributions for right now, because that part is tricky enough. So I threw those two predictors in. We're still in logit land. Here's my output. So Pearson chi-square thingy is down to 15. Not better, but not good enough. So let's see if we can do better. There are two ways of modeling over dispersion in binomial data, additive or multiplicative. Additive means I put in person as a random effect. That is a concept that we have not talked about. Conceptually, it is putting in what is supposed to be residual variance into the model as another variance term. That's what's happening. That's the only way that I know how to do it in multi-level data, is to do this trick. So there's a variance across persons as a random effect, and under dispersion now, results are different. And then we got to this thingy. So additive over dispersion I learned about 2 years ago. This is the thing I learned about 10 minutes ago. This is beta binomial. I'm still struggling to understand the parameterization of this model, to be honest. But I can understand conceptually what it does. And it allows the variance to exceed the mean. In the same way that negative binomial has a stretchy factor, it gives you this phi stretchy factor that does the same thing. So it doesn't just dump extra variance into the model. It dumps variance conditionally on the mean. So as the mean, it will be highest at a probability of 0.5 and lower on the edges. That's what the variance function does. So this allows it to grow over that. Yeah, question?
So would you say this is better than the previous one? Because it allows for fluctuation?
It's a multiplicative enhancement to the variance as opposed to just dumping more variance in the model. So whether it's better is an empirical question. Probably.
Okay.
Yes. Yeah, the dumping thing in is like a Band-Aid on it.
Yeah.
We can check distribution fit. We cannot check AIC and BIC though, because those are based on different likelihood functions. They're not on the same scale. There is a test that wouldn't work for this. I tried to get it to work and then gave up when I was struggling too much, but it's called the Vuong test, V-U-O-N-G. It's a person that it's named after. That's supposed to be a way to compare fit of different kinds of distributions. That's a thing you can do. But this one is not available in the software that we've been using. I had to hunt for it. So I downloaded something called BetaBin, a user-defined package. I believe it's the people who wrote the Stata textbook that's the optional book for this course. It's their package. And it came with a couple other ones that we're going to explore. And I found the beta binomial distribution in proc finite mixture model, of all things in SAS. Although proc finite mixture model does not have anything else that I want, like contrast estimate statements or LS means. I couldn't figure out how to do multivariate wall tests, for instance. So what did we get? This thing right here, it does for you. This is a likelihood ratio test. Do you remember those? We talked about those a while ago. Do you want to review those? Would that be good? Okay, let me pull. I think it might be lecture 1. I have a slide on that. Nope, that's an example. It's either 1 or 2. I know it's not this one. Let me see if I can find it real quick. My computer sounds like it's about to die. Like, ah! Yep, here it is. This is slide 18 of lecture 1. I'll put it up for reference. So log likelihood is height. It is the sum across persons of their individual heights given the model parameters, where the formula for height is your distribution. There's a different formula for height under the normal distribution than under Poisson, than under negative binomial, etc. So that's why we can't do anything regarding log likelihood values to compare across distributions. They're on different scales. It's like inches and centimeters. But what we can use this for is to test differences among nested models. So in your output, Stata does this version of the test to get the significance of the model predictors. I've been having you ask for wall tests instead to be consistent across all the iterations of these different packages. It takes the difference in height between nested models. So the log likelihood of the model that has fewer parameters minus the log likelihood of the model that has more parameters. Take that difference and multiply it by -2. So SAS does you a solid by giving you the -2 attached to it already so that you can just take the straight difference. In Stata, you have to do the difference times -2 yourself, but Stata has a thing to do this, likelihood ratio test. That difference is supposed to follow a chi-square distribution. So even though the absolute value of log likelihoods and -2 log likelihoods don't help you at all, their differences do. So if you add one thing to the model, the chi-square critical value for that 1 degree of freedom, the number of things added, is 3.84. So your difference has to be bigger than that to be significant. This test will show up for later in the semester for any kind of nested model comparison involving variability instead of fixed effects. Whether we need extra variances, different patterns of covariance across multivariate outcomes, these tests are used for that. So because we're talking about the need for a variance, we have to use a likelihood ratio test. It's the most proper way to do it. A wall test is not proper for anything involving variability because variability is bounded at 0. So this is what Stata is doing for you in this piece of output right here. So let me take this and decompose it. Likelihood ratio test of sigma equals 0. Sigma is my stretchy. So the difference between a model that does not have it, which is the regular flavor binomial, and this beta binomial flavor model that does have it, the difference in their -2 log likelihoods is 997. That's a p-value that is 0 to very many decimal places, but more than 3. One technical aside that I'm debating how much time to put into this in your homework, but since I'm talking about it, I may as well. This thing right here, chi-bar instead of chi-square. Do you know what the difference is? We haven't talked about this, but you've seen it maybe in other contexts. It's referring to the fact that the proper chi-square distribution to compare this to is actually a mixture of chi-squares with degrees of freedom 0 for when the stretchy factor would have been negative, which is impossible, and chi-square with degrees of freedom 1, which is when the stretchy exceeds 0. Whenever you're testing a parameter against a boundary as the null hypothesis, you're supposed to use a mixture chi-square distribution instead. Practically speaking, in this instance, what it means is that you get to cut your regular p-value in half, because there is no such thing as a chi-square distribution with 0 degrees of freedom. It doesn't have any area. So whether or not the difference in terms of the critical value, if you add one thing, if you use the correct mixture distribution, the critical value for adding one thing is 2.71. If you use the naive 1 degree of freedom, call it good, the critical value is 3.84. So it does not make a difference in this context.
So say it was like 0.1. You could divide that by 2, is that what you're saying?
You can cut your p-value in half in this instance, because it's a comparison of a mixture of zeros and ones. 0 can't happen.
That would be fun, yeah.
You can, so I usually don't want to explain this to reviewers, and so if I don't have to, I don't.
Okay.
Right? If it would be significant either way, I'm like, it's degrees of freedom 1, I'm not going to talk about it. If it's right on the border, then you have to explain it, but it's going to be a marginal effect in that case anyway. Let me show you a picture. This is like my greatest hits collection. I'm pulling up all of my other classes. Longitudinal. Let me pull up lecture 5. That's where it is. That's a biggie. It's towards the back. I know exactly what picture I'm looking for. Let me show you the difference in the chi-square as a function of mixture versus regular. Right here. The picture on the left here, do you see the tiny little difference between these lines? That's what we're talking about. I've tried to care about this, but I just can't. I'm sorry. But in case reviewer 3 wants you to use a mixture distribution, that's the difference. The way that you can do it in practice, and yeah, since I'm making a big deal out of this, I'm going to have you do it in your homework. I just decided. So let's say that we have a chi-square of 4. All right? Chi-square of 4. I have degrees of freedom 1. P-value. So this chi-square is the difference in -2 log likelihoods. Okay? I'm going to do a function, chi-dist in Excel. It wants the chi-square value and the degrees of freedom, and it returns a p-value. Okay? To figure out what the mixture chi-square would be, there. It's like, there's no p-value for degrees of freedom 0. That's not a thing. Noom. It's very angry. Noom. So this is 0. A mixture p-value is 0.5 times the p-value that you get with this distribution plus 0.5 times the p-value you get with the one that's 1 less. So 0. So it works out to just take your p-value and cut it in half in this one case. Are you laughing?
Yeah.
Noom? Is that it? Well, that's what it says. Hashtag Noom. It's very angry. Yeah, because it's like...
That's what I'm going to start thinking about.
Anytime you think about that,
It's very angry with you, yeah. So this it just works out to be 0. That's what it is. You will also see this for mixture of 2 and 1. Then it's not so simple. It's not always take it in half. But for this one instance, it is. Okay, there, I just covered it. You guys are going to get to practice with this. It'll be fun. But yeah, this is the background. So the critical values are just slightly different, especially for 1 versus 2. It's 5.14 versus 5.99. So Stata is doing the correctest version of this. That's why they call it chi-bar and not chi-square. And where the degrees of freedom would normally be, they have 2 numbers in here. It's a mixture of 0 and 1. That's what this means. But either way, it is much bigger than the critical value, so yes, we need this. So beta binomial is better than binomial. That's what we know. In SAS, they don't give you Pearson chi-square over degrees of freedom. They just give you Pearson chi-square. So I had to divide it myself. That works out to 0.75. That's the one that's supposed to be 1. So it looks like this is definitely better than binomial. Based on just distribution fit, it looks like it's better than the stick some extra variance in it approach also. And then this is where I think we left off. Okay. Zero inflation. Do you remember talking about this in the context of counts? Yeah, the same thing is true in binary outcomes. You can have 0 inflation. However, in my data, do I have 0 inflation? Go back to the picture. I have 1 inflation. Could I figure out how to make the software do 1 inflation instead? No. So what did I do? Reverse it. Yeah. So the next set of models, I'm modeling number incorrect. Taking this picture, flip it. Because it does look like there's more people here than what a beta binomial would suggest to me. So it's a testable hypothesis. So that's where I'm talking about extra zeros. This is slide 9. So now we're back into a situation where we have 2 submodels going on at the same time. We have what's known as a zero inflation model, and we have the regular model. Hang on. There's a typo. That should be logit, not log. Find and replace error on my part. So we're going to have a regular model that predicts the proportions using some flavor of binomial. And then we're also going to have a separate submodel that predicts the logit of being an extra 0. You can put predictors in it or not, as you see fit. Unfortunately, this is the one that's really hard to interpret. The hurdle variance would require some kind of 0 truncated distribution, which I couldn't find anywhere, so I decided not to even try to do an example with that. But it looks like this. If I switch to number incorrect. Note to myself, I learned this 10 minutes ago. I'm not even going to try to get the notation right. I'm just not. I punt. I know what the model says, though. We have the same model for the proportion of any trial, but now we're predicting it being incorrect. So higher scores are worse. And then we have the probability of being an extra 0 has only an intercept. So what I'm trying to do is figure out if I need the extra 0 inflation model. If there are these extra zeros such that I need a separate submodel to accommodate them.
Wait, how is the intercept?
Hmm?
How is the intercept?
How big it is. It's going to give me the logit of the probability of being an extra 0. So when we did this with counts, do you remember that we had a logit of minus 22 with the standard error of 45,000? A logit of minus 22 is basically 0. So that is the probability of, it corresponds to the probability of being an extra 0, meaning we don't have any.
Oh, so because it was previously one.
It's because it was really super small. So that's what I'm looking for here. What is the probability of being an extra 0? If it's super duper tiny, I don't need it. So then the mean that I get out of this, conditional mean for, here's another typo, fix incorrect, that's what we're predicting here, is the proportion of any one trial, the probability of any one trial being incorrect times the number of trials, but now it's being weighted by the probability of being an extra 0. So it's going to bring down the mean to have this extra 0 inflation model in here.
If you need it.
If you need it. So in Stata, the same thing that I downloaded to do beta bin is ZIB, that is zero inflated binomial. So I-link here does not refer to inverse logit or inverse link. It refers to the inflation model. So I'm telling it that I want to predict the probability of being an extra 0 using a logit link. I'm using the logit link also to predict the probability of any one trial being incorrect in the other model, the one that we've been focusing on up to this point. And then in the inflate model, I have only a constant, only an intercept. So it's an empty 0 inflation model so that I can see what is the probability of being an extra 0 and do I need to worry about it. Okay. Are you with me? You want to hear any of that again?
So for this one,
Yeah, okay.
it's different than the previous one because you're writing 2 separate lines.
It's different
We're
than,
having, like, before I feel like we only had linked in one link.
right,
Okay.
yes. It's different than what we did before because before we only had one model.
Okay.
And the model was predicting the probability of any one trial being correct. So now we're predicting the probability of any one trial being incorrect and another separate model that predicts the probability of being an extra 0.
So say you wanted another predictor in that inflate model, you would put it within that parentheses?
Yep. Yeah, there's nothing that stops me from taking these things and plonking them in there. Yep. They can't call you now. I'm about to see if we need extra zeros.
So does the inflate model always have to be second? Because that's always right, because you write the first one with it.
Does it have to be second?
Yeah, I guess for me, when I see that, I think of like the outcome and the predictors that are linked in the end. But then for the second one, it's not written the same way.
This part is what we had before. That's predicting the primary submodel.
Okay.
That's the probability of an incorrect response.
Okay.
So that part is just, other than the switching from correct to incorrect, that part's the same. This is the new part that picks up an extra submodel to predict the logit of the probability of being an extra 0. Isn't this fun? Makes my head hurt a little bit. Wake up, Terry.
I'm here.
You're here.
Waiting for SAS.
You're waiting for SAS. All right, I'll bring you the SAS. Finite mixture model. That's what it told me to do. I looked for an example, and this is what it told me. This syntax makes no sense to me, but this is how you ask for a 0 inflation model. It wouldn't let me stick predictors in it. I know. So either I don't know the right way to put them in, or it just can't handle that capability. But you can do it in Stata, and I tried it, and it worked. Okay, so here's my output. I have no idea, based on Stata output, how well this model fits. No idea. Right here, this is your likelihood ratio test of the two predictors. That's what that means. Do you see how it says chi2 with 2 in parentheses? That means regular flavor chi squared with 2 degrees of freedom. The reason that regular flavor chi-square is okay here is because what those 2 degrees of freedom is referring to are these 2 slopes in the incorrect model. These slopes have a null hypothesis of 0. They can be positive or negative, so we don't have to do any special mixture things. The walled test that I asked you guys to do via test, this thing right here, that chi-square value is different. It's down here. 126 versus 116. These things are supposed to agree asymptotically if you get a big enough sample. This sample is actually pretty small. It's just 97.
So what does the likelihood ratio test tell you that's different from the other thing?
It tells you the exact same thing through different math. There is a technical description of the differences of these in one of the early chapters of the textbook for this class. There's basically hypothesis tests like this. There's 3 things you can do. You can do a walled test, and that's the estimate divided by standard error is a t or a z. And if you're testing more than one thing, you don't want the estimates to cancel each other out, so you have to do it in a squared metric. That's where we get to chi-square f. Remember? So t is to f as z is to chi-square. Remember the difference? Nope. Denominator degrees of freedom. Remember t is like flatter than, yeah, it's like squishier. Yeah. So if you have infinite denominator degrees of freedom, infinite sample size, that's z. If you're assuming that it's some kind of not infinite, that's t. Those are for testing one thing at a time. If you want to test more than one thing at a time, then t becomes f. T squared is f if it's only one thing. And z becomes chi-square. But f and chi-square are in squared metrics. So this thing right here just refers to the joint hypothesis test of these 2 things by comparing the difference in -2 log likelihood across these models. This is a walled test that does the same type of idea just with different math, and the third one is a score test. That one doesn't show up very much in these types of models, so I haven't talked about it. But if you want to hear the technical differences between them, that is it. In practice, you can always do walled tests. You can't always do likelihood ratio tests. We'll talk more about that when we get to multivariate, why that is. But walled tests cannot be screwed up. That's why I teach them that way. Anyway, what was I doing? This thing. Inflate. That's the logit of the probability of being an extra 0. What is that probability? SAS gives it to me directly. It's 0.4. That's pretty high. It's not 0. But remember, this is the binomial model that didn't fit in the first place. So the last one I wanted to try with this is the beta binomial with 0 inflation. So stretchy distribution and extra zeros at the same time. Still got to correct that same typo. So switching out this one instead of Zibin. 0 inflated beta binomial. And in SAS, it's switching from binomial back to beta binomial. So now this model has both a stretchy factor that allows the variance to multiplicably, is that a word? Multiplicably? Someone. Multiplicably? That's not right. Multiplicably. Well, I need an adverb, damn it. It makes it multiply it.
Yeah.
Multiplicatively. Okay. Yeah, the variance is multiplied. There. So it has the log of the stretchy, it has the stretchy, and then it has the inflate probability. So after allowing stretchy, the probability of being an extra zero is actually smaller. It goes down to being 0.25. And so according to SAS, the previous model did not fit. The chi-square over degrees of freedom was 2.34 when it's supposed to be 1. In our new model, it fits better. It's 0.878. That's the closest to 1 that it's been all day. So that one fits relatively best. And here is putting predictors inside the inflation model. Can't do it in SAS, but I can do it here. Come back. Here we go. Right here. So now there's two different sets of predictors. The thing that I've highlighted is predicting the logit of the probability of being an extra zero. Do you see any significant predictors of the logit of the probability of being an extra zero? Here's your p-value column. You see anything significant here? No. So, yes, there are extra zeros. It looks like there's about 20% of the cases are extra zeros based on the previous model, but I don't know why they are. Okay. I have a comparison of all the fit statistics here. We have the ones with predictors don't add anything in terms of AIC and BIC, and this one is the one that fit the best. Stata wouldn't give me a Pearson chi-square over degrees of freedom, and I didn't try to calculate it from the predictive model anyway. And here are some words. Ta-da! Yeah, the things that I learned 10 minutes ago, I've never actually seen a results section for. So this is just my best guess at what it would look like. So same structure as before, intro paragraph that describes the modeling approach and the software, the sort of robustness paragraph about all of the different distributions that I tried and why I decided to go with the one that I went with, and then what actually happened as the third paragraph here. And no, you're not going to do homework on this. If I learned it 10 minutes ago, that hardly seems fair. All right. So that's the end of this set of stories. Questions? No. Good. Well, I will fix the typos and repost this thing later today. So binomial type proportion things is one kind of other flavor of not normal. Here's some more. What if they're continuous values, but they're skewed? So this is slide 10. Things like response time, outcomes involving money, how much something costs, or salaries. Those things tend to be positively skewed, and they can't go below 0. There are two distributions I want to introduce you to for these, log normal and gamma. So these look similarly shaped to Poisson or negative binomial, but they're continuous distributions, meaning therefore outcomes that take on values that are non-integer. We're going to keep the outcomes to be predicted positive with a log link, and that means that we can do e to the slope as odds ratio type things that are called incident rate ratios for that as well. So here's what log normal looks like. You're going to like this one. Do you know why? All you have to do is log your outcome, and it's the same damn thing. So this is the one instance in which transforming your data is actually okay, as opposed to picking a model. This is it, the one. The only catch is that because of the log link, you have to remember what happens to the slopes. So if you fit a linear effect of a continuous predictor, for instance, here on the x-axis predicting log y, when you unlog the predicted values from that slope, they take on this sort of exponential curve instead. So that's the one trick. But basically what we're saying here is that the log of the residuals are normal. Yeah.
Just to clarify again, the difference between log and logit is because the log is when it's bottom of the
At the bottom.
and then logit is the.
Yes. Yeah. Logit is for upper and lower boundaries. Log is for lower only. And if you had something that somehow was bounded upper, I think you'd have to reverse it to be able to use these things.
Oh.
Like only upper. I've never seen something like that. It's possible theoretically, but you'd have to reverse it so that it's bounded at lower to do these things. So let me show you. I have a new story to show you that has this one. It is example, not my longitudinal class, back to this semester, 3B. I stole this data set from your textbook. It's sale prices of homes. So we're going to predict how much 100 houses sold for based on how big they are, how many bedrooms they have, how many bathrooms they have, and whether or not they are new construction. There. Here's what this outcome looks like. The normal curve over that, what do you think? Does that curve match? Not at all. In addition, we have what appear to be about 7 outliers in terms of price. So this is sale price in terms of like $1,000. So like here's a house that sold for $580,000. Here's one that sold for about $500,000. So if you saw this distribution and you had never had this class, what might you be tempted to do to fix it? Delete them.
Just run it.
Just run it and don't have any distribution fit to look at, and then it's fine, right? Yeah, that's one answer. That's one answer. What about trimming outliers? Dump them. Okay, who are your outliers? Where are you going to cut this off at?
The last 3.
The last 3?
Interquartile
These
range,
ones?
sure.
Yeah.
What about these guys?
They're fine.
Oh, they're fine. Okay. Well, thank goodness. Yeah, so outliers, some function of interquartile range.
Yeah.
I learned that like 25 years ago. It's gone. But yeah, so here is interquartile range. Here's a box plot. So the median of the distribution is the line here. The mean is higher than the median, which is an indication of positive skewness. And this is the reason, by the way, that it's typically median home price that's listed as like a descriptive statistic for these sorts of variables, because home prices are unbounded in positive land. Yeah, I gotta tell you, when we were shopping for houses here, we did so on the internet before we moved, and there was one house in particular that it was a football coach's house that was for sale, the Iowa football. It was $1.6 million.
Did you get that one?
You know, like we got sort of like, I'm tired of looking at things we can afford. Let's just see what the most expensive house for sale in Coralville is, right? And it was 1.6 million. And I'm looking at it like, there's a walkout patio from the master bedroom to the pool in your enormous backyard. And there's like marble, and it's like the basement had a actual bar. Like you go to a business, like that kind of actual bar, and a urinal. A urinal in the basement. For all the football players who come over to watch movies or whatever, they have a urinal.
Like 2 months out of the year.
I know, but I gotta say, I looked at these pictures, and his wife was an interior designer, and it was just the most beautiful thing. And I'm like, So a monthly payment of 1.6, like, okay, if I do like a 60-year mortgage with interest only, yeah, we ended up not looking at it because it would have been too hard. But I had that, it is actually, I think.
Has the price dropped at all?
I believe it's down to 1.3 the last time I looked,
That's a
so,
lot for us little folks.
That's a
yeah.
lot more reasonable.
Yeah, I had to do the mental calculus to be like, no, Lisa, stop. This is bad. You're gonna be eating ramen noodles like at your bar downstairs, right? This is not good. But point being, houses are unbounded. That's where I was going with this.
You could even eat ramen.
It would have been a very bad financial decision. Yeah. So one quartile range. So this thing is the maximum value below 1.5 times the interquartile range above 75%. So like by that definition, these things are all outliers. Everybody over here, they're all outliers. So do we dump them? These are houses. Like these aren't errors, right? Like the $1.6 million house is real. There's pictures of it online. There was a virtual tour that you could walk through. So it gets really tricky to try and justify dumping data, right? Just because you don't like it. So I'm going to give you some options for sort of addressing the skewness of this distribution, but then I'm going to give you something that is completely different that is designed to reduce the influence of outliers. Funny?
The house.
The house. Did you find it?
We think perhaps. And it's just outrageous.
Does it have a walkout pool from the master bedroom? Because I don't know a lot of houses.
This one has a slide.
It's, yeah.
And a gym.
Of course it does, right?
And this one's 1.4.
And then it's like definite professional photos. I mean, somebody tuned in.
There's an aerial view.
Well, for that price, there better be, right? Yeah, no. Dream big. Dream big, friends. Yeah. You're not wrong. Yeah. So I don't want to dump these houses. I want to live in them instead. But that's for another day. Because you're right. We would get like 1 week out of the summer would be warm enough for a pool. Yeah, we looked into that. So here are some choices for modeling stuff. And one of them is literally just F it, take the log. Done. It works out. Since we're running out of time here, I will just foreshadow what we're going to see. It works out that if you fit the log normal distribution in a generalized linear model, or you just log it and put it in a regular regression, everything is identical. Exactly the same thing. So in reality, in practice, that advantage is going to be really helpful for when we need to have more complicated models, like multivariate models and stuff like that. Just being able to log an outcome and have it fix problems of non-normality, that's a really not helpful thing. So, all right. But that's where we're going next time. The other thing I'm very excited to teach you, which I learned about 8 years ago. So we're getting back now. But definitely after graduate school, was something called quantile regression. Have you guys heard of that? Heard of it? Do you know how to do it? It's cool. It's super cool. So that's quantile regression. What we're going to learn how to do is design for this problem of outliers. Because what it allows you to do is predict the median instead of the mean. It is. And while you're at it, you don't have to pick the median as the 50th percentile. You can pick any percentile.
So it doesn't even the median, it's just
Any,
Gotcha.
yep.
No.
Yep. They call it, it's really percentile regression, but for whatever reason they call it quantile. Because you can pick all of them. Wait for it. See, I'm getting you guys to come back next week. That's what I'm doing here. Yes, we'll be one step closer to $1 million house. This is a picture of what the model parameters are in predicting every single quantile.
I don't even know what that means.
Well, come back. I'll tell you. It's a way to ask whether the effect of a predictor is different for different levels of your outcome. So for instance, in this story, one of the variables is going to be square footage, because that's important in buying a house, right? That affects the sale price, I should say. Here is the plot for square footage. Zero's down here. So it has a significant positive effect the whole time. This is a confidence interval. But it looks like, just eyeballing this, the slope starts to trend upward in the more expensive houses. Like if you're trying to predict a house at the 80th quantile or percentile, the slope is higher than if you're predicting a cheap house down here. So square footage matters more at certain points on the house distribution. Cool, huh? Ugh. Okay. Well, that'll be next week. So, and then we're done. This is gonna not like class is overdone, but like that's all the kinds of outcomes that I know of in life. Then you know what we get to do? Play around? Not quite. Play with data. You keep doing that. No, we're going to switch to multivariate models with all this stuff. And path models. Yeah, so repeated measures, dyadic data, family data, learning how to test mediation in all of these outcomes. Mediation is regression with a much better marketing campaign. We'll learn how to do it. You know how to do moderation already. Mediation, you can do mediated moderation, moderated mediation, and you can do it all no matter what kind of outcome you have. It's going to be cool. So yeah, come back. Come back next week. We'll be one step cooler. Okay. Any questions before we adjourn? All right then. Have good weekends. Get outside and enjoy the warm weather. And I will see everybody later.